Good morning, good afternoon, good evening, wherever you are. My name is 𝗖𝗔𝗥𝗕𝗢𝗡. I am the CEO for Carbon Solutions LLC. Today, I'm going to talk about our tool, SCO2T Pro. It's a rapid tool for geologic carbon sequestration, science, engineering, and economics. First, a little bit of background. We know that CCS is basically part of every clean energy pathway, and that we will soon need to be capturing, transporting, and storing hundreds of millions or billions of tons of CO2 each year. And we need a support framework, a decision support framework to help with that. And that framework is called SimCCS Pro, and part of that is the SCO2T model for sequestering CO2. At the bottom left, you can see the visibility that we've generated for the SCO2T Pro toolset. And on the right-hand side, you're looking at the kind of image that we have worked with for partners to generate, in this case, with the Great Plains Institute for their report, the transport infrastructure for carbon capture and storage. And so we can deploy SimCCS Pro on a very large scale to understand where and when we should capture, transport, and store CO2. And the key part of that is the storage piece, and that's where SCO2T Pro comes in. So here's a schematic of what the SimCCS Pro toolset looks like. At the center, this hexagon, you have the SimCCS Pro decision optimization engine, and then you have a capture, transport, and storage model parameterizing that decision support engine. And the model that supports it on the storage side is called SCO2T Pro, and we can use it as a standalone tool as well, and that's what I'm going to talk about today. One of the things you'll hear me keep reporting is that SCO2T Pro does dynamic CO2 injection, dynamic plume evolution, and couples that with sequestration economics. And we would claim that it's going to be the world's most advanced tool to do that. And I'm going to talk about it today and show you what it does. First of all, very quickly, SCO2T Pro is an Excel-based tool. It has thousands of lines of code behind it. It is powered by machine learning and AI. The reason for putting it in Excel is, in addition to having all of this code, all of the data is in the same place, and anybody can run SCO2T. All they need is a Mac or a PC, and you don't need to install anything whatsoever. You put in a range of geologic inputs into SCO2T, and it will calculate these key outputs: dynamic injectivity, storage capacity, plume dimension, CO2 density and brine production, and ultimately connecting that to sequestration economics. And the key reasons that we use this feasibility level tool, SCO2T, is for reservoir screening. We can do sensitivity analysis, which I'm going to talk about a lot today, and uncertainty analysis. And ultimately, we can apply it to large regions such as the United States. And one thing you'll hear me repeat on the next couple of slides, it's a very rapid tool. It does between 5,000 and 10,000 realizations every second, and they're just as accurate essentially as a full hydro code. First of all, let's start with kind of the AI machine learning that's powering SCO2T Pro. Our goal was to create a tool that can replicate a hydrogeologic code, something like 𝘖𝗔𝗥𝗕𝗢𝗡 from Los Alamos. And the way we do that is, in this case, we used 𝘖𝗔𝗥𝗕𝗢𝗡 from Los Alamos, and we did 10,000 detailed realizations of CO2 injection and storage and plume dimensions. And using those 10,000 brands, we could use it using machine learning to train reduced order models, and those reduced order models we build into SCO2T. When we started this project, the very first thing we did is we created a very large Monte Carlo deck. There's 10,000 brands. And so on the x-axis, what you're looking at is the 𝘖𝗔𝗥𝗕𝗢𝗡, the actual injection rate that came out of our full physics simulator. And on the y-axis, we're looking at the predicted, the reduced order model, or the SCO2T prediction of what CO2 injection looked like. And we're looking at a very large range of CO2 injection rates here. It's kind of complicated, but the reason we need to do this is to understand plume dynamics across all possible geologies. So when we first ran this, we got a typical one-to-one scatter plot, which you're looking at here, and you run the basic statistics, and you see the R-squared is 0.99. You say, hey, this is great. This is a fantastic model that we produced. But what we found is, when you started to dig in, we do need the whole injection rate, but what we're really concerned with is that injection rate between 0 and 1 million tons a year. That's what realistic injection rates look like with realistic engineering of wells. And what we found when we dug into that 0 to 1 million ton region, that the reduced order models had basically zero predictivity, even though across the whole range, the R squared is 0.99, it was basically zero for the region we were interested in. And the novel way that we developed to address this, and you can see it in that Frankenstein's monster paper I have in the bottom right, is we break the solution space into multiple different injection ranges and reduced order models. Here we're looking at just 4, there's actually 7 in the Scott Pro currently. And what you can see is for each injection rate, they do very, very well for their specified rate they're trained on. So the green dots are looking at a reduced order model trained just between 0.1 and 1 million tons a year. And you'll see those green dots are really on that one-to-one line. But once they go outside of that range, you start to see that they do a really terrible job and we can't use them. So now we have these 4 to 7 different reduced order models. They cover the whole range. We have to come up with a way to predict which reduced order model we pick, and you can read more about that in the paper. But basically what we end up is this kind of curve where we could Frankenstein together these different reduced order models to cover the whole injection rate. And so what we're looking at, the gray dots was that original reduced order model we built with an R squared of 0.99, and the color one-to-one line is what we ended up using. And those gray dots had an average absolute mean error of over 200%. The Scott Pro reduced order models right now have an absolute mean error of less than 4%. So we've gone from the average run taking something like 5 hours in FEHM, and we can replicate that by doing 5,000 to 10,000 realizations a second. So here's a little bit on some of the sensitivity analysis we can do with Scott. The first one we looked at, and you can see it much more information in the paper we just published in Energy and Environmental Science. You can see the first analysis, sensitivity analysis, was on depth. So we ran Scott between 1,000 and 5,000 meter depth. We held all of the other information, constant, thickness, porosity, permeability, and the geothermal gradient, to see what happens when we change the depth. And the first thing that happens is you get the results you see in the literature. As you go deeper, the properties of CO2 become more favorable for CO2 injection and storage. The injection rate goes up, the plume radius goes up, the storage area density goes up. So the deeper you go, the more favorable sequestration is, except what we found with our tool is, again, we wanted to limit the injection rate to a maximum of 1 million tons a year. That's what's realistic given current well engineering dimensions. And once you limit it to 1 million tons a year, as you go deeper, the injection rate goes up, you hit this 1 million ton a year limit, and things change. No longer going deeper is better for you. And so these red circles are showing you that inflection point. So for example, once you hit 1 million tons a year, we now see in the top left chart, the green dotted line is flat, but the blue radius starts to go down as you go deeper. And then how the impact of that is, looking at the bottom left chart at the blue line, the number of wells changes, and ultimately looking at the bottom right chart and that inflection point in the red circle, the costs actually go up. So before we published this, the literature suggested as you go deeper, favorable CO2 properties lead to favorable CO2 sequestration economics. In reality, this is not true if you limit the injection rate to 1 million tons a year. Second sensitivity analysis we did was looking at thickness. What happens if you hold everything else the same, but you change the thickness of the formation? What we found is that the plume radius doesn't change much. The CO2 spreads out to the same place it did, but you see injection rate goes up because the formation now is much thicker. And ultimately what you see in the bottom right is that your costs go down. So you want to be looking at thicker formations. So this isn't necessarily amazingly novel, but I'm not sure it had been shown before. But the key thing that we brought out of this was, here we're looking at the 2D output from the FEHM model, just to show you how, as you increase the thickness of the formation, the plume extent doesn't really change that much. But you can see how the plume fills out, and that's why we have this preferential benefit on the cost of storing CO2. I'm going to run through the permeability and the porosity sensitivity analysis really quick. Here we are looking at permeability, and it's a bit like the depth. As you increase permeability, the CO2 injection rate goes up, the plume radius goes up, and ultimately what you'll see on the bottom right-hand side is that the costs are better, the more permeable formation you have, you can inject more CO2. But again, once you get to that inflection point where you see those dotted lines appearing in the top two charts, where you can no longer go above the 1 million tons a year, you do get an impact where costs actually do start to go back up again with these really highly permeable formations. But if you look at that chart in the bottom right, yes, the costs go up, but maybe they only go up $1 a ton or something. And so it's not as dramatic as the costs went up with formation depth. For porosity, it acts like you might expect it. The more porous the formation, the more pore space you have to store CO2 in. So the injection rate doesn't change with porosity if you look at that top left chart, but the plume radius does. The plume now doesn't spread out as far as porosity increases. There's more pore space to store the CO2. And ultimately what you get looking at the bottom right figure is that your costs go down the more porous the formation is. In this case, we cannot hit that critical point, that inflection point of 1 million tons a year, because porosity is not impacting the injection rate. The final sensitivity analysis we looked at was geothermal gradient or temperature. And one of the things that maybe people didn't realize before we did this, the balance between CO2 density with temperature and pressure, the deeper you go, well, in this case, the geothermal gradient's going up. The higher geothermal gradient, it actually increases CO2 storage, and your costs generally go down because you have favorable injection and storage properties of CO2. But one thing we found here, what we're able to do with Scott, it's an operational tool, and if these 3 red circles you're looking at, if you do not extract brine or you do not treat, there's no cost to disposing or treating the extracted brine, increased geothermal gradient is good. However, because as you go down deeper, CO2 density changes, you're producing more water by volume for each ton of CO2 you put in. If you have to treat that water, and you can see where we just added on a hypothetical $1 or $2 a cubic meter to treat that brine, the costs go up. So again, this is the idea that once we can capture the physics, the dynamics of injecting and storing CO2, we can couple that to economics, we start to see some novel things. And so whether you treat the extracted brine or not has a really big impact on whether geothermal gradient is a good thing or not. So the last couple of slides really quickly, the Scott Pro, we showed the sensitivity analysis. The other thing we can do it is we're building the Scott Pro database, geologic database for the US. And so we can apply the tool for anywhere across the US. And here we're looking at a preliminary map of what CO2 sequestration storage costs look like across the US. And so we can start to use this tool for understanding regional impacts of CO2 sequestration. And getting to the final slide, we don't just have the cost, we have the storage as well. And so what we're looking on the left-hand figure is the Illinois basin, where the height of each one of these bars is proportional to the CO2 storage, and the color of the bar is proportional to the cost. And so we're really able to do this at the feasibility level, take a really quick look at what CO2 sequestration could look like across large areas. We're doing this just for the US. And so to wrap up, the take-home message here, and I've kind of just summarized the bullets on the right-hand side. We've built the first tool that captures dynamic CO2 injection, plume evolution, and coupled that to economics. Other tools that try to do this do a volumetric analysis, and so they aren't close to us in terms of costs and estimates of capacity. So we can do this for large areas. You can repeat this tens, hundreds of thousands of times because you do 10,000 realizations a second, and you can look at uncertainty, you could look at sensitivity. It's an operational tool. You can limit the injection rate to 1 million tons a year. You can change the well spacing. You can let plumes overlap at the site. This is an operational tool. It includes treating extracted brine. And I would finish off by saying it enables a new understanding of sequestration science, particularly when we're trying to get to this level of injecting, storing hundreds of millions of tons or billions of tons of CO2 each year. So again, my name is Richard Middleton. I'm the CEO of Carbon Solutions LLC. You can see our website. You can send us an email if you'd like to hear more about this. Thank you.